So I'm working on this audio compressor circuit in order to achieve automatic gain control with audio signals. And this is based on a Rod Elliott design of a diode-based voltage-controlled attenuator. And so in order to test it, I've built this, and I'm going to put it up in a separate video of how I designed it and everything. But in order to test this, I'm using a signal generator from my oscilloscope, which generates a 2.5 volt peak-to-peak sine wave here. And, I could generate it at any frequency, but because the oscilloscope is a 5 volt device, I could only get it to work at 5 volts peak to peak. And so in order to be able to attenuate a truly loud signal, I can't really test my audio compressor using this. And so while it works to attenuate the signal, as you can see in some of the tests when I adjust the threshold here, you will it doesn't give me a true picture of how well this works. And it occurred to me that it's time for me to design my own sine wave generator in order to properly test this circuit, something with a much larger voltage span. So this video is about designing a sine wave generator. So you may recall using this particular circuit, which is a bridged T network, when I made the drum machine. And what this does is basically using an op amp, and in the negative feedback of an op amp, you have a bridge T network with capacitors and a resistor to ground and a large resistor bridge going across that. And when you apply a trigger pulse to the non-inverting input, you get this decaying sinusoidal wave, which basically acts like a kick drum or a tom drum for a percussion circuit. However, when you modify the bridge T network and put a feedback some of the output into the positive or non-inverting input of the op amp, you can avoid having to trigger this, and it allows for a continued oscillation at the frequency determined by the resistors and capacitors you have in the negative feedback loop. So using this formula with values for R1, R2, C1, and C2, you can calculate frequency or design this circuit based on a frequency that's desired for a sine wave. Or you can make it adjustable with a potentiometer at the bottom, as I have here. So in my particular case, I designed a 200 or so hertz signal sine wave generator. So I made this sine wave generator using an op amp, TLO74, and basically for a bridge T network. Basically I have here two capacitors in series. In the middle of them is a 10K resistor going in series with this 50K potentiometer. And I have positive feedback, 20K resistor from output to non-inverting input, and a 1K resistor going to ground, basically a 20 to 1, and then a 1 mega ohm resistor that is bridging the ends of the two 27 nanofarad capacitors. And basically this is providing a sine wave, and this is all in the negative feedback circuit of the op amp and the inverting terminal. So, and you get a very, very steady sine wave, and that changes based on this potentiometer. So if I change it, it's going to increase the frequency or decrease the frequency. Here I'm increasing it by increasing the amount of resistance. We're actually decreasing the amount of resistance. Here it goes up to 50K. I bet I could get it higher, but it's a little bit distorted at that point. But here's a pretty smooth 30 hertz sine wave signal. And I'm going to use that as a function generator to test out my little compressor. This is, since it's getting positive and negative 12 volts at the rails, this gives you a pretty strong voltage. You know, it's 20 volts peak to peak. So let's scale that down before we input into our device. So now I took this sine wave generator circuit, and the output of that is going to a buffer, an op-amp based buffer, and that buffer is putting an output to a 100K potentiometer, which is wired as a voltage divider. Basically, the output of the buffer is going into the upper pin, pin 3, the other one's going to ground, and the output is going to the oscilloscope. And so now I could take a 10 wave or 10 volt or 20 volt peak to peak signal, which you could see here at the maximum point is 20 volts. And now with the turn of the potentiometer, I could scale it down. And this is a 200 hertz sine wave. I could scale it down to a very low voltage, which is, let me increase it so we can see it. I could scale it down to nothing. But here, you know, you can see the peak to peak voltage there pretty readily by just a turn of the potentiometer. So this way, I've made my very own sine wave function generator, and you can change the frequency on it by varying this potentiometer. So it's a little finicky on the breadboard, but there it is. So let's make it 1.5 volts peak to peak. That seems like a good number to start with. We have this 1.5 volt peak to peak circuit. I've now taken the output of that, in addition to going to the oscilloscope, I've taken it and put it through a 1/4 inch jack and go into a speaker. So let's hear what it sounds like. And that's what a 1.5 volt peak to peak circuit sounds like with minimum amplification. If I increase this, it's going to get louder and softer. And at this level of amplification, I sort of stop hearing it at 500 volts peak to peak. It's very quiet now. So 1.5 volts peak to peak. I also don't want to blow your guys' ears out. So it works. So now that I have my little sine wave generator built, which is scalable, I'm going to test my compressor circuit, which is based off of a diode bridge. And so you could see here on the oscilloscope, the yellow tracing is I have them to the same scale. The yellow tracing is the input waveform, and the blue tracing, because it's on a breadboard, is an output waveform, so it's a little noisy. But if you can see, the input waveform and the output waveform are basically about the same. Right now I have it set, I have the threshold set so that the output is about 2.5 volts peak to peak. So based on this waveform, if I change the threshold here, it's going to provide the changes in the waveform. So let's say that I want it just a waveform, just at 2.5 volts peak to peak. Let's adjust it close enough. And 2.48. Now, if you look at the total peak to peak voltage, 2.2 volts there on the input waveform, and it's giving me an output of 2.5. If I scale down the input waveform, the yellow tracing basically keeps it, more or less at 2 volts peak to peak. If I increase it to, say, 6 volts, 7, let's change the scale here. Let's make it a big wave. Let's make it max. So max is 20 volts peak to peak, and it only goes up to 3 volts peak to peak on the blue tracing. So let's scale it down, but generally it keeps it at that level. It's only when so basically it's not going to go much beyond 2 volts peak to peak. So let's put it on the same scale now. Let me decrease it. Stays basically the same. Stays basically the same. So this is, and the compressor circuit decreases the dynamic range and finally gives me the holy grail of a semblance of automatic gain control of a signal. So I can keep a signal whatever level I want it at, and it's not going to change around with the volume. And if I wanted to listen to the signal, I would get a, let's see, let's put that there. And let's put, I want the output. So that's the wrong spot. All right, here's the output. Okay, so now parent wave is 6 volts peak to peak, and I'm going to be listening to the output. Let me turn on the speaker. So that's what a 200 hertz sine wave sounds like, and let me, not much change there. And if I go way up, volume doesn't really shift that much. Barely audible difference in volume, at least to my hearing. I don't know if you guys can sense the difference, but that's the difference. So I gotta say, this little compressor circuit works just fine. Let me turn that off. And thanks for watching.